It's not easy to come after Florent's talk, which I found fantastic. And in particular, of course, my slides are much less fun. So remember, I will finish what we were talking about, this tensor PCA thing. I remind you what we're doing. Oops. Interesting. Shit. No, this is because we worked hard to have this on this subject here.
That's pretty good. That should work.
Okay, better? Okay. So we were somewhere, we mentioned this question about detection for tensor PCA, and then the different question, recovery, computation, and all that was explained. I mentioned the gap. So remember what we had here, that the statistical threshold for MLE was the same as the IT threshold, so there's nothing to gain there. MLE is good. And then there was this question, and this was done using this Katz-Rice formula, which I reminded you last time. And again, there was this gap. This is interesting. So first the Katz-Rice picture, which I draw on the sphere here. Let me just remind you, this establishes a link between random matrix and this problem, because the only thing you have to look at is the distribution of the Hessian conditioned by a point being critical. And this is essentially, in this case, a GOE spiked. And the spike comes from the signal. Okay, so that's the link with the BBP transition that we had seen before. So that was for this picture. And then there was the question of algorithms, and then there was this gap. Remember, this means that computationally things were harder. You needed way more data, and then I explained that, in fact, you could do a little bit better if you are much smarter than gradient descent or even approximate message passing. And but this could still, if you really like gradient descent, you could still reach the best threshold by, for instance, using this replicated gradient descent thing by Giulio, Chiara, and Valentina. Okay, so let me explain how this is related to this. I was fast a bit. So when you compute the MLE, the likelihood, or the log likelihood, what you obtain is just this. That is, so you remember this U is the spike you're trying to find, and then you have this TIs, which are your thing. And so when you expand this thing, what you find is your empirical risk is this plus that. And okay, of course here we had M sample, but you could assume, because everything is Gaussian, you could assume that M is 1 by just changing lambda to lambda times square root M. So when I was telling you that this lambda, the signal to noise ratio, also measures the number of data, there is just by this ratio square root M. If you assume that lambda initially is 1, then your lambda becomes just square root M, square root of the number of data. And then of course here, you can assume that this unknown signal V is just E1, which in my picture I put as the North Pole. And then this thing just becomes lambda U1 to the P plus this. And remember, these guys are Gaussian. So after normalization, as I explained before, this is the P-spin Hamiltonian, and then you add this, so this random homogeneous polynomial, to which you add a non-random fixed polynomial, which is this one is very complex, as I've mentioned before, many local minima, etc. This one is very simple. You add the two. When lambda equals 0, when lambda is small, of course, this one wins. When lambda is larger, this one will have a role, and this is the transition I just explained. Okay? So, and of course, when I was mentioning so now what you have to do is to compute the distribution. This is a Gaussian function, obviously, because these guys are Gaussian. And you have to compute the Hessian of this, conditioned by the fact that this function is critical. And believe me, this is what I was telling you, the Hessian of that is of course a Gaussian matrix, which is a GOE spiked. And the spike comes from here. If lambda is 0, you have no spike. Okay? And so that's what I was saying. This is the P-spin. So the question is, does this likelihood function stay complex when the SNR is present? Okay. And then, of course, we want to understand if the global minimum of this thing is close to the signal, which is to the North Pole here. That was the whole question. And so this function is very complex, exponentially many local minima, exponentially many critical points of all indices. And the question is, where is the global minimum? And so, as I said, use Katz's Rice. This is what I just mentioned. And the question just becomes this. Where does the top eigenvalue of a spike GOE get out of the bulk of the spectrum, which is the BBP? And this question was, in fact, asked. This is what I wanted to mention by Ian Johnston, a statistician. It didn't come from random matrix, right? Theory per itself. You know, sometimes things are presented, mathematicians do this, and then it's useful for that. What a surprise. It's not a surprise. Random matrix, in fact, was born with statistics. And this question was asked by a statistician, Ian Johnston from Stanford. And this is where we did it with in a different context then, but it was essentially continued by Sandrine, Mireille Capitaine, and Benaïs George, Delphine Ferral, Catherine Donati-Martin, and others. Okay, so in fact, the important result that we need here, I don't want to get into the computation, you can look at it. In fact, when you look even at the pure p-spin without a drift, without a signal, the question in random matrix that you need to have to solve this question are the following very quickly. You need the concentration of the distribution of the bulk at a speed faster than n. That is, you need that a probability that the bulk is far from the semicircle to decay like exponential minus n to a power more than 1. Okay? That's what you need. That it concentrates faster. That we knew in this context for GOE because we have this large deviation principle that we established with Alice a long, long time ago, which is in the rate n square. The probability that the bulk of a random matrix is far from the semicircle is like exponential minus n square. So that was what we needed. But then you need something else. You need something about this top eigenvalue. So there were large deviation of the top eigenvalue for a pure GOE. That was also a work with Alice and Amir Dembo, and by the way, which was motivated already by dynamics of spin glasses, and which is in a scale n. This is what we needed. Okay? But then here we needed more. We needed a large deviation for the top eigenvalue in the BBP phase when it's far, right? And that was done by Mylène Maïda. At this point in time, I think she was doing her thesis with Alice a long time ago now, 13 years ago. So everything was on the table. This paper is pretty simple. You just use what's on the table. The total complexity then is always exponential in n. And this is what I was saying. For this model, the picture I was giving you, you cannot get rid of the critical points that are around the equator. The ones that are in the mediocrity phase, they are always there. This function will not trivialize in the sense that all this will disappear, whatever the strength of the signal, essentially. And so there is a value with the normalization I had here, which is 1. When the signal is larger than 1, you have a ring of critical point which appears at positive latitude, closer to the signal than the equator, and that contains the absolute minimum. And the number of critical points there is sub-exponential. And when lambda grows, this latitude goes to the North Pole, as you can expect, and then the MLE converges to the signal. And this is what is called asymptotic strong recovery. This is weak recovery. Okay? That you can see in the landscape of this thing. Okay, this is the picture I was giving you last time. Now, here's a quantitative result. Here's the result that we have with, I don't know what, there should be a comma here. It's May, Montanari, Nika. In 2018, so we find this. We have a large deviation. We have this large deviation result, if you want. The anneal complexity, the log of the mean number of critical points. M is just the sphere here with values in E, and it's given by some variational formula. We have a lower bound and an upper bound. Note that we don't give here. I don't give you the thing with fixed index. Okay. This is done for the pure p-spin in this paper with 2013 with Aufinger and Czerny, where we have a really neat trick to do this with a fixed index. Here we didn't do it. If somebody wants to work, this is interesting. Okay, it's not done in this paper. And so the function, if you want to see the formula, here it is. It's a little bit like when Florent shows replica computation. Here it's what it is, and then you can analyze this and you find the picture I was telling you. Note this term here. 1/2 of log of p minus 1. Right? Remember when I told you the complexity was... Okay, so we have something for local minima. That is done, but not for every index. And so this is the interesting transition for local minima. Let me explain that quickly. There is something bizarre happening here. When lambda is smaller than a certain lambda 1, there is an exponential number of critical points in a band near the equator and nowhere else, as I said, right? You have this thing around the equator where all the mess is. Then when lambda grows, below lambda 1, this band grows. Then at some point, between lambda 1 and lambda 2, you have critical points that appear at a positive latitude. Okay? But the absolute minimum is still at the equator. So this is a crazy phase, a crazy thing, if you think of it. It means if you do maximum likelihood, if you were the god of optimization, you would find your absolute minimum, the maximum likelihood estimator, and it will be at the equator, which means completely not informative. Nevertheless, you have critical points and local minima, which are in fact good, closer to the signal. Okay? So that's what this says. It seems crazy. Okay? But it's a fact. Now, when you go above this second threshold, then you have the minimum which is achieved up there. The maximum likelihood estimator is up there. And so it's correlated. It's weak recovery. So what you can check it at the second threshold is the IT threshold, lambda 2 equal 1. So when you can detect, MLE does it. So this means that this thing is a complete fluke. Right? This thing is below the IT threshold. Right? It looks like there is information here. There are, I tell you, find critical points. So here's what's wrong with what I'm saying here. Find critical points of this function. And some of them, local minima, some of them will be very correlated with the signal. But it's below the IT threshold. So what I'm saying cannot work. So why is it? And nevertheless, everything is a theorem. Things are true. It's just because, of course, here I know that the North Pole is here, and so I can detect this little circle of things that are close to it. But if you don't know where the North Pole is, you don't see them. Some of them are close, but you cannot find them. Okay, you don't know where they are. Okay, because here, the rule here above lambda 2 is easy. The rule is find the absolute minimum. There are some local minima that are good, but which one? Okay, so it looks like this contradicts that, but in fact it's not the case. Okay. And of course, when lambda tends to infinity, this latitude is going to go to the North Pole. Now, let's talk about, so I'm saying this slide is called, as I said before, now you've heard my message. Complexity is not the only hard problem. You also have recovery, optimization. So the optimal threshold that I was mentioning, so you can, this is done in this paper, Algorithmic Threshold for Tensor PCA, which just appeared with Reza and Okosh, which was done 2 years ago. And this paper, which is more recent, last March, for online SGD. Here we did gradient flow and Langevin and gradient descent. And this is really heavy mathematically. I don't want to, it's serious analysis here, stochastic analysis. You have this process, you want to understand what it does. Okay, maybe I would not advise to read this thing. In particular, we introduced an infinite series of conditions that we have to check. So it's really painful. This one is much simpler. SGD, online SGD, I was asking what are the advantages of SGD? One, so what we prove here is that SGD works as well as the rest. One advantage is that this paper is easy, right, compared to the other one, which are super painful. No, but it's not 2003. This is the archive number. This is March to 20.
Oh,
I see. That's just, I don't know. Okay, so these algorithms, the most important thing, this threshold here, it's important because what I explained, escaping mediocrity. And so let me now explain, oops. So if the drift induced by the signal is too weak, the algorithm will linger too long near the equator, which is what I drew last time. And then will be trapped by complexity. Then complexity will be important for refutation. By the way, there's a very recent paper with Alex Vine and Ilyas Zadik, which we posted recently, which gives this kind of refutation for another problem, very different from this one, for sparse PCA, but with the same kind of spirit. Okay. So now let's generalize. Enough with the tensor PCA for the moment. Let's take I mentioned the GLM. So this is the work with I'll describe a little bit the work with Antoine Maillard and Giulio Biroli, and then also this work with Reza and Okosh on the dynamics of this. So this is exactly what Florent was describing. Okay, these are IID, some M of them, and this is one loss function, which is not a loss. This is just and then the real loss that I was looking at here is an L2 loss in the case where you have a planted signal, right? So this X star is what you want to, let's say, a unit vector on the sphere that you want to understand. You don't know it, and this is the L2 loss, okay? So that's exactly the thing that Laurent was explaining, but here with the real nonlinear phi. It's not a kernel, it's not a random feature, it's really a teacher-student network, okay? With one node. So here, if you assume again that M is alpha n, this is exactly what Florent was explaining. And these two random loss functions, this, let's say L2 at least, cover many well-studied estimation problems, depending on which activation function you choose. You could have linear regression, this is what Florent was mentioning, phase retrieval, I say here phi quadratic, but it chose phi to be absolute value, but it's the same spirit. The compressed sensing, logistic regression, GLM, which go back to these two guys in statistics. The teacher-student network, which is the same thing as a one-node network. So this model is not a real neural net. It just have one node. But it contains most of the things you see in statistics. And that's the thing we can do. And this is one of the questions I asked. Understanding the complexity of that is doable. But now if instead of one node you have many nodes and a serious one hidden layer neural net, we don't know how to do that. So I just mentioned one piece of literature on this thing. And so the first question, again, we've seen this type of function. What is the complexity? And then what is the performance of the optimization dynamics? So this is this work. So this work with Giulio and Antoine is not completely solid mathematically. There's a little difficulty there, which is a pain in the neck about log of determinant. So this is being fixed, but essentially, of course, the result is correct. And then the question two is how hard is it to find the minimum of this thing with whatever you want, gradient descent, gradient flow, SGD, online gradient descent, when you initialize them randomly. And this is the paper I just explained, I just mentioned. Okay, so complexity. So what is done in this paper, the ratio of n and m is, as in what Florent was explaining, fixed, alpha. And then assume that the data is Gaussian, which is ridiculous, okay? It shouldn't be, but that's the only thing you can do. Why? Because I want to use Katz-Rice. And as I mentioned already, when you want to use Katz-Rice, the only version of Katz-Rice that is available really in the literature is for Gaussian functions or for functions of Gaussians. And this will be a function of Gaussian. It's not a Gaussian function, it's L2, for instance, loss, but it's a function of Gaussian. So that's why we assume that the data is Gaussian. Anybody courageous enough to go back to the proof of Katz-Rice and do it for non-Gaussian, say with smooth density, something reasonable, would have immediately an enormous benefit because all these things will be valid for non-Gaussian, but I'm not courageous enough. So the simple extension of Katz-Rice, as I said, I think it's done in Azais and Schwebor in some appendix, gives you this for functions of Gaussian. And so what is the random matrix question that you use? You get to when you use this dictionary. It's, of course, now no longer a GOE, but spiked Wishart matrices. So I write them like this, or Pastur-Marchenko. This is, unfortunately, Alice keeps saying she doesn't like Wishart matrices. This is, in fact, equivalent to what she was doing, but she wrote it the other way around, right? She wrote S, Y, Y star, S star. Of course, if you just do it like this, you get Y star, SS star, Y, which is the same as this, right? So, I'm sorry? Yes. Okay. So, but of course, here this D will be the covariance of something, so it will be non-negative. In fact, it will be diagonal. So here, this is the same model. Trust me, this is just an obvious thing. And this is well understood by Pastur-Marchenko. Wishart, of course, did it for D to be identity, again in 28, because remember now our X is Gaussian. So this guy is, of course, not a Gaussian matrix. And so now the thing that we will have here, our D will be diagonal. X is Gaussian. But this diagonal D will essentially have only a few entries that are not 1. Okay, that's the spike thing. In fact, only 1 in this case. Okay? And so the spectrum of this matrix is well understood when the empirical measure of the entries of the diagonal converge. This is what the theorem that Alice mentioned. This D, again, is SS star in her notation, essentially. It is linked, of course, to free probability. The limit is the free multiplicative convolution of this asymptotic spectral measure and of the Marchenko-Pastur distribution with ratio alpha. And now what we have is that we are spiking our matrix by a rank 1 perturbation. So that, H is D here. So this diagonal is just essentially identity with one term, which is not 1. That's the spike. And this is, in fact, the origin of the BBP transition. In 2005, the question asked by Ian Johnston was about exactly this, not about the GOE. The GOE came later. GOE didn't have much of a role in this kind of linear regression type problem. Okay, so in this paper, we compute this complexity. And the variational problem, so I say we will soon be able to. I don't know, this is kind of bragging, because I'm not sure, Antoine, I'm sure, is not working on that. I'm not either, so you're welcome if you want to do that for fixed index. Okay, so, and so the result are, let me show you, L1, who cares? So the result of the same form as the one I gave you for tensor PCA, the variational thing, the number of critical points, is a soup of something. H is the relative entropy of this nu. The nu here is, in fact, you should think of it as the, okay, it's a variational parameter, but it's an infinite dimension. It's a probability distribution. And this is the thing that you are optimizing about. T1 is rather difficult in the space of probability measures. I will describe it right now. Here it is. So that's not too hard. You still have K1. K1 is the logarithmic potential, which is here. So, what? What am I saying here? Phi is fixed. I'm sorry? Phi is the activation function that I had before. This phi here. But what the constraint you have here is just that the semi-roll of phi against nu is in the set of values B that you want. Okay? But anyway, so you have this. And this mu nu here is the Pastur-Marchenko distribution, the one that, in fact, Alice introduced. And whatever. It's given by the free multiplicative convolution of the alpha Marchenko-Pastur distribution with the image by the second derivative of the. Okay, so needless to say, this is an enormous mess. And it's hard, of course. What we haven't done is to understand anything about this variational problem except very simple things. So one can check the very simple thing that. There was a question? I'm sorry? Yes. Oh, you're worried because Relou is not smooth, but you don't really need to be smooth everywhere. You. Right, yeah.
If the function is constant,
Yeah.
in some region, then you cannot have that because L1 is not there.
Yeah.
But absolute value is fine.
Absolute value is fine.
Yeah, of course, I didn't explain. I already mentioned before that in order to apply, Katz Rice does not apply to the picture that where you have very flat region. That doesn't work. So indeed, you cannot do that with Relou. Okay, so, but anyway, so you can check that the complexity is in fact 0, happily, for linear and quadratic activation. So those models are not complex. And you need, the question is for what activation are these models complex and how to compute this complexity. And now you have to solve this variational problem.
Quadratic activation and absolute value activation is kind of the same thing. So there's
No, you will see, yeah. So, no.
I think this is
This is,
simply looking at L1.
this is L1. This is not yet L2. So the L2 loss is coming. Yeah. So L1 was just, in fact, L1 was just the function itself. I was looking at the complexity of the function, not of the loss. I didn't have put any loss there. So here, forget L1, this is L2, and you have a formula of the same type. L1 is just the function, sum of phi of xi mu dot x. Okay? And that's the complexity we're computing here. Now we're computing not the complexity of the function, but of the L2 loss. That's L2. Okay? So that's, this one is even worse. So it's there, very involved functional. And the formula are there. You know, this is really equivalent to the crazy formula that Florent was giving about replica. You look at them, they are whatever they are, except that here we are not able to analyze them, that you have this variational problem and they are terrible, except in simple cases. Okay, and the functional is this mess. And this K2 is again a logarithmic potential, as before. Well, this. Okay, so enough. I will skip that. Okay. Oy, oy, oy. Okay, so now let's go to, so the complexity is there. I expect the complexity, I mean the problem, the anneal complexity. The one thing to do is to understand that for critical points, and the other thing is to really understand the variational problem. And the next thing, if you really want to do something serious, is to do what Eliran-Subak did. That is compute the quench complexity. Okay, as I said, we have a quench complexity formalism in the physics paper with Giulio and Chiara and Valentina, but for a math proof, you have to compute the second moment typically. It's rather difficult. Again, it's just a matter of having enough energy, and you're young enough, maybe you want to try. So let's come back. So I imagine that we have in this context for this L2 function, for instance, we must have something of the same type that we had for tensor PCA. That is, you will typically have complexity around in the random region around the equator, and then at some point you should have a transition which corresponds to the. I don't know if this transition will correspond to the IT threshold, like in the lucky case of the tensor PCA, where you have the absolute minimum, the critical points, the important ones are close to the North Pole. And in this case, I don't expect that in general you will have zero complexity on this good latitude. It could be that you have positive complexity like in the P plus K model. Okay, so let's come back now to the dynamics of optimization. So again, the question I ask is, first, finish this thing about GLMs, and second, go now to a real network. Right? Maybe a one-layer network and do this. Okay, and that, even with Gaussian entries, that will be difficult. Okay, so no, no. What I'm saying is the first thing is to understand this variational problem. Typically, a thing which is not in the kind of expertise of this kind of crowd, including myself, because this is really a variational. I mean, once you have the variational problem, is how do you find the minimum? That's a difficult thing. But even getting a formula for a general one hidden layer network is, we don't know how to do it. Okay, that's complicated. And that would be the first step to understand the complexity of those networks. Okay, so you see at the moment we have this kind of one node network, teacher-student network, however you want to call it, or GLM, which are, as I said already, pretty general, but they are not the real two-layer thing where you begin to have machine learning. Okay, so let's go back to this abstract formalism of empirical risk, because that's always what you will have to do. And again, I had fixed the n as the dimension of the parameter, called x here instead of theta, d the dimension of the data, and m the size of the sample. So we have these three examples. Remember, spin glass, tensor PCA, and GLM. Now, what is the performance of dynamics to go down this thing? So I already gave you what we can do, but I want to go much further now. So first, let's go back to dynamics of simpler things, which are maybe simpler. Spin glasses. So for spherical spin glasses, you do Langevin. For hard spin, you do Glauber, and this has been studied forever. So Langevin is, of course, just this, when H is your Hamiltonian. And this double, here on the sphere, this would be Brownian motion on the sphere. And the mixing time of these dynamics is typically exponentially long at low temperature. So you have, for general dynamics, Glauber or Langevin, whatever, you have a result, for instance, in this paper with of Reza and Okosh, and then of Okosh and myself, where you have conditions to have this mixing time to be exponentially long. So this is exactly what you don't want to have in optimization. And so, of course, in these very long time scales, you have all sorts of things happening, aging, and all sorts of funny things, but which are not, which, of course, you want to avoid. That's exactly, you never want to be in this regime when you do optimization. And so, okay, that's typically how aging happens in spin glasses. In the spherical case or in the Glauber case, the configuration stays stuck in deep traps or exponentially long lengths of time, which are essentially, the time you spend in traps are essentially the time it takes to find them, right? Which is also exponentially long. And then the motion, and then you, of course, between two such traps, you find time in many other traps, many other wells, which are shorter. So in this time scale, it doesn't count. Even if you spend exponentially long time there, if you spend exponentially 2n in this one and exponentially n in this one doesn't count. And the motion among the trap is called the fractional kinetics, and the aging follow what is called the arcsine law. That is well understood. In fact, one of you asked me about trap models. I gave a class in Les Ouches something like 10 years ago on this, on trap models, which is easy to find. So this has been done first for REM, and then for P-spin, and this is kind of understood. In fact, Langevin dynamics for spherical spin glasses is not really understood mathematically. It should be, but it's not. And this was, in fact, the original motivation of the work on complexity, at least for me. That, again, is just a matter of having enough energy to do it. It's not completely easy because you really need to understand all the communication, all the Morse complex of this function. How you go from a certain type of minimum to another minimum, by what kind of critical points do you go through, okay? But now you want to look at shorter times. So shorter times has been, which is you let n tend to infinity first before letting the time tend to infinity. So for instance, you can look at chapter 5 of Mézard, Parisi, Virasoro book, the Bible and spin glasses. And of course, the work of Sampolinsky and Zipelius in the 80s for the soft spin SK, Cougliandro, Kurchan. We've worked on that a long, long time ago. As Florent said, you know, at the beginning of time in the 90s with Alice. And so this Alice and Amir. And there is recent work by Amir, Eyal Lubeski, and Ofer Zeytouni, which is interesting there. So in this short time regime, the religion that you learn from physics and that we tried to adapt then was that the important thing is to study two time functions. The correlation between the state of your system at time t and at time t plus s. This has a limit, a thermodynamic limit, that and the response function associated to that. And this, you can close the equation using this. That is, you have a limiting equation, nonlinear pair of equation between C and R, integral differential equation, pretty painful. And then the next thing is to understand the long time behavior of this thing, which is what was done there. Pretty difficult mathematically, but this gives a picture of what happens for this short time aging in some sense. The behavior of when you let first n go to infinity and then t go to infinity. This has been the religion since the 90s at least. And this could really not be used in the context, let's say, of tensor PC or whatever. Okay, let me forget this. What we had to do here in this work, and the way to analyze this was to, and starting with spin glasses, was to say enough with the physics religion. Let's not compute two-time function. This is, maybe this closes, but we just can't do anything serious with it. Let's compute, like, a very ignorant mathematician, one-time function, right? And just choose them well. And look at the evolution of this thing. So the one-time function, you could look at the value of the energy, the function you want to minimize, at the position of your algorithm. You could look at the norm of the gradient. And these, for instance, are the things you may want to understand. But of course, you hit the snag that was hit by physics a long time ago, which is that when you write those equations, they never close. Right? They never close. So you end up having an infinite hierarchy of equation, which is a pain in the neck. Why would physicists not like it? It's because they wanted to close equation. Physicists like equalities. So when you take two-time function, you can close equation, and that's it. What we did here was really what mathematicians do, which is simply, okay, we can close the equation, we can close the equation. We can still use inequalities rather than equalities, right? And obtain results. And this is what we did. So it's a little bit of a pain, as I explained. So it's pretty heavy. So this is developed in this paper called Bounding Flows for the P-spin model, published 2 years ago or something. And in order to control this infinite hierarchy of equations, which this is the price to pay for not closing the equation, as Cugliandolo and Korshan and others. Florent, help me here. Who are the others that I'm missing for this? Okay, anyway. Very respected and respectable colleagues in physics, whose name escaped me now. So if you don't want to close the equation, then you have this to do that. And of course, what you will obtain is less precise. If you obtain inequalities, you will just have bounds instead of exact things. But this is enough to draw conclusions. What can we draw as conclusion? We can prove that in finite time that you can control, the system will end up, let's say for our spherical spin glass, for the moment you don't have any signal, you're just moving in this crazy landscape of the spherical spin glass. In finite time, for Langevin dynamics, let's say, you will end up in a region where the energy is low, proportional to the ground state, right? So maybe in finite time, you will get to 70% of the ground state. I don't know, the best you can do. But of course, it will still be above what I call the famous dynamical threshold, okay? But it's also a region where the norm of the gradient, this is the most important thing, is bounded below. So all along your trajectory, the norm of your gradient is bounded below. All along this trajectory, you don't come close to any kind of critical points or critical region, because the norm of the gradient is bounded by 1/2. Yeah?
What is the dynamical?
Oh, in my picture here is what I call negative E infinity, the place where the saddle points of finite index begin to appear. And it's known, and it's called a dynamical threshold in physics. It's known in physics using the Cugliandolo-Korshan approach, for instance, that if you do finite time, you cannot go below this, right? And you understand why, because if you go below that, you begin to get into the place where you have plenty of local minima, and there you can be stuck for much longer. Okay? So The important thing here is that you can prove, without using Cugliano-Quotient, that in finite time you can go low, very low, and you don't care about complexity. So this thing is telling you, everything I've been telling you about complexity for this is irrelevant. Then, of course, complexity, in order to feel complexity, you need much longer times. So you go down deeply and you know completely the complexity. Okay? That's for Langevin dynamics. Then we applied it for tensor PCA when you add a signal. You do the same type of techniques for Langevin dynamics and gradient flow. And in fact, it's a more general class, but let's do it like this. And you have the same thing. If you do Langevin dynamics or gradient flow, you, from a random initialization around the equator, quickly you will correlate. You will end up in this weak recovery phase if the signal-to-noise ratio is large enough. And this is the number of data has to be larger than this, which corresponds to the ratio I gave you, lambda larger than n to the p minus 2 over 2. Because remember, there was a square root. So, and the reason why you needed all that, as I explained, so we also have a refutation. That is, if you're below the threshold, as I explained, you will get, you will not do that. You will not correlate with the signal. And this, this online gradient descent is what I'm explaining now in this, I mean, it's this more recent paper. So let me explain this now. So again, maybe I didn't explain last time. Why is it hard to escape? So what I'm saying here is that the tensor PCA is hard, right? Why is it hard to move in this direction? Remember that the function you were looking at was lambda x1. X1 is this axis, right? That's the null spin. X1 to the p plus a spin glass, right? So what is the gradient of this, right? The gradient in this direction, of course, is simply px1 to the p minus 1 with the lambda plus the gradient of this. And of course, the Hessian will have here, in this direction, you would have p minus 1, x1 p minus 2. Okay, that's for the Hessian. I'm just differentiating x1 to the p. That's not hard. Remember that my p is larger or equal to 3 here. So the gradient at the equator when x1 is 0, the gradient is 0. And when you're close to the equator, this thing correlated with the signal, this thing, of course, will be the gradient of an isotropic field. The spin glass is completely isotropic. So this one has really not much chance to point to the North Pole. Okay? This doesn't see the North Pole in any way. It's just isotropic. Same thing for the Hessian here, which essentially be a GOE. So when you have this spike here, near the equator, the tensor is 0, and even in the Hessian you have 0 here, when p is larger than 3. So there's really nothing, neither the gradient nor the curvature of the Hessian, that pushes you in the right direction. And as long as you are very near the equator, typically when you start with a random point you are near the equator, this thing will be small. So in order, if your lambda is large enough, which corresponds to have enough data, then you can compensate for that. Okay? If your lambda diverges with n, like an n to the p minus 2 over 2, then this would become strong enough to push you away fast. That's essentially what we do. And then when you do that, then the rest of the proof is what we do here seems very simple. You want simply to say that the motion becomes a one-dimensional motion. You just look at the component x1, which is the latitude. How does this evolve? Right? And essentially, it evolves according to this. And if you have to, when your lambda is large enough, you will just try to neglect this random thing. Show that the random thing doesn't hurt. Right? That's all. That's what you have to do. So it's a very natural result that I was telling you. And this threshold is just, essentially, as I explained, the best you can do. Okay? So the reason why it's hard to escape mediocrity is this. Okay? It's because you have here, your function x1 to the p has its x1 to the p with p larger or equal to 3. So that its derivative and its second derivative are 0 in the region of maximal entropy. Okay? We will call this, in general situation, we'll call this the information exponent, and this is this classification that I want to describe in more general things than the tensor PCA. So let's take back our let's say GLM or general things.
I think it was kind of YI without IID, but
Yeah.
the Y also, does that include the input data and the labels?
Yeah, you could, in this notation, you can put input and output. Yeah.
But then the labels are IID from the input in your case?
No, no, it's the XI, YI in your notation that would be IID, and these are.
No, so the Y, they don't depend on the X. I mean, we
No,
have-
they do depend on the X. You don't care. They're IID. As XY as a n plus 1 tuple is, you have a collection of IID things like this, but you can have a relation between Y and X.
IID, I from I.
Yeah, I from I, of course.
Okay,
Of course,
okay.
of course. Okay, so let's see what happened now when we want. So again, I said all the difficulties we had to understand complexity of general models. But this optimization thing is, in fact, very general. And so let's describe this. So you take, here I take the simplest of all algorithm, online gradient descent, given here. It's on the sphere, so what I do, of course, I do a step. Okay, and then I just project back on the sphere. Okay, to stay on the sphere. I could do, I could take the spherical gradient instead of the usual gradient, and that would not be very different. Okay, so, and you start with a certain distribution for x0. So that's the initialization, that's the algorithm. And, okay, so here is something. So you take the true population risk, the one that you would want to minimize, you can, and you assume that m equal alpha n, and and it's not hard to see in general, for instance, for Gaussian things, that, so you expand it like this, okay? A little bit like what Florent was doing. These VK are, depend on the whole thing. So, and this M is the correlation, it's the latitude, it's the correlation with the spike, or the overlap with the spike.
So you do have spices, so your input data,
Yeah.
your data are from features.
I have a spike, okay, and in this L, for instance, you would, here I'm in the spike model, so this L would be, for instance, the L2 norm with a spike, okay? So,
Sorry, it's not like the spike model, like the tensor spike model.
the spike model of the tensor is included in that. You could do that too. Right, you assume that there is a ground truth, that the X star that you don't know, it's planted, okay?
Yes, but I mean there is a difference between the spike and the TLM in the sense that in the TLM the X star would be creating the labels, whereas in the...
Yeah, you're right. It's just a matter of notation. But yeah, so maybe I should have done like Florent did. I should have a loss like this of a function like this of the xi, right, and the parameter, whatever it was, and the yi's, right? But I just put everything together. It's just a matter of notation, but it's just exactly the same thing. Okay.
So you have the YIs that are created.
Okay, I should not have called them the yi's. In your notation, you have the xi, the yi's, okay? That's, but the ground truth is given by one parameter, x star.
Yes,
Theta
the
star, if
labels
you want.
are given by theta star. And
Yes.
some activation.
And some,
that is
exactly,
ground truth,
exactly,
the feature activation.
yes. So it's exactly the problem that was mentioned there. So now I'm on the sphere, this function, I expand it like this, and this is the latitude, and you call capital K, we call it the information exponent for whatever reason, the first thing such that this thing is non-zero, right? So again, remember what I was explaining. If capital K is 1, it means that the gradient at the equator is non-zero. If capital K is 2, it means that the gradient is 0, but the Hessian has a direction which is non-zero in some sense. And if capital K, oh yeah, because maybe I should say that. In the spike tensor case, this true population thing is just this function, right? Just lambda x1 to the p, right? So capital K tells you whether it's like, when capital K is 1, it's like x1. When capital K is 2, it's like x2, 1 square. And when capital K is larger, it's like x1 to the k. So this capital K is like this p, okay? And so this assumption is verified for both tensor PCA and general GLMs. That's what I'm saying here. This is not completely obvious, but for tensor PCA it's obvious, but for general GLM, it is doable. Hermite polynomials again, hidden somewhere. Okay, so we need technical assumption on the initial measure, which are satisfied by a random initial start. And some smoothness, let's forget the smoothness thing. And then we can prove that the online gradient descent recover the signal partially in time t, which is which is over the order of m. Of course, remember here that in the online gradient descent, each step corresponds to one data point, okay, with the right choice of alpha, amount of data, and of step size. But, so what is the right choice of alpha? So the simple case, you have three classes of models that corresponds to k is 1, k is 2, and k larger than 3, larger or equal to 3, which we call easy, critical, and hard. Okay? So hard, tensor PCA is obviously hard, because p was larger or equal to 3. This explains the gap. This explains why we needed this n to the p minus 2 over 2. But there must be lots of models that are easy. In fact, it's hard to find hard problems. So if you take an easy case, k is 1, what you need is alpha just larger than a constant, and your step size smaller than a constant. That's a very simple case. You just need the amount of data you need is of the order of your, alpha is a constant, like what Florent was explaining. So that's the simplest case, and you don't need a tiny delta. And then you will partially recover in this general. K is the first, in this context here, it's P. It's when you look, okay. You expand the true loss function as a function of the latitude, right? Which is of course the case here. The true loss function is just this, okay? Because the expectation of that is 0, okay? And then you look at the first coefficient, which is you do a kind of Taylor expansion, and you look at the first coefficient that is non-zero. So again, k is 1 corresponds to this thing being linear near the equator. K is 2 corresponds to this thing being quadratic. K larger than 3, more than cubic. And cubic are always the problem. Okay? Quadratic and linear are simpler. So what I will explain is that, oops, I'm going in the wrong direction, is that k is 1, the linear case, is easy, k is 2 is critical, and k larger or equal to 3 is hard. Okay? So, okay, so
Constant here? Is it something in the proof, or would it in reality just be like any alpha that is bigger than some infinitesimal epsilon would be?
no, you need, I think you need, there is a constant. The one we get is not necessarily the best in any way, but I think you cannot take alpha go to 0 in general. That's what you're saying, right?
Yeah,
Yes.
to me it seems like yes. If you have the linear case, then any.
Anyway, the way we control it, because it's not purely linear, remember, it's not linear. It just starts as linear. Okay, so then to control the rest, we need alpha to be positive.
Where does this bound on delta come from?
I'm sorry?
Where does this upper bound on delta come from?
From the proof. This is, I'm hiding the proof here, right? You can take, so you need you don't want to take size steps which are huge. So, but here what I'm saying is that this is very reasonable. You can take a size step which is, you don't even adapt it through the thing, which is just bounded above by some constant. You don't have to take it very small, right? That's what I'm saying. So this is good news for the algorithm. Delta smaller than some constant rather than delta smaller than 1 over n to some power, right? Where it means that you would have to take tiny, tiny size steps. Okay, the critical models, when k is 2, so when the linear term is absent, then suddenly you need more data. You need alpha to be log n squared. That's bad news, but that's still okay. It's log n. Okay? So if alpha is less than that, we have refutation. Okay? Of course, our constant is not necessarily the best, and we don't want to work on the best constant. And same thing now, but you have to, you can recover if you, but you have to, at least for the proof we have, you have to have a size step which is small, like 1 over log n squared, okay, which seems reasonable. And then, so this critical models means you can escape, but you need, remember the gap? But in this case, we had the number of data we needed was n to a power, p minus 2, right? Here we just need log n squared when it's critical. When it's simple, you need nothing, just alpha, at least as much data or a fraction of the data you have. Okay, so, and then the hard models, when k is larger than 2, then you need alpha to be larger than n to the k minus 1. Okay? So that's really bad news. You need a lot of data. That's exactly the case of tensor PCA. Right? The number of data you need to diverge polynomially. So here in tensor PCA, this k would be p. Here you get n p minus 1. And you remember that if you just do the little translation, this corresponds to the amount of data that you want to be p minus 2. Because alpha is, anyway. And your delta needs to be very small. I wrote it wrong. It should be negative this. It should be very small.
I was going to say that for the critical case, the alpha doesn't need to be greater than. That's just something also coming from the proof.
I'm not sure. I should check. We have refutation. I don't know if we refute that hard or not, but I would be prudent on that. You can convince me, but I'm not sure. I'm almost sure that you need something diverging.
The sign, yes, but the alpha, the delta needs to be like that. Without the square.
Okay, but we just, okay, maybe you can play on one of the two. Okay, so there are plenty of numerical experiments that I wanted to quote here, but before that, let me explain. So, wait a minute, should we have this? No, so it's too bad I didn't put that here, so I will explain now. So what are the, in this class of, so I just said the tensor PCA is obviously there. What are, in the different models I've mentioned, the one that fall into easy, hard, and critical. So remember, to stay in this class of model like the tensor PCA, you could look at what I call the P plus K model, right? Where here you have a P spin, but here you could take a K or a Q, I called it. Right? Then depending on P and K, you had different regime, but of course, what defines now the hardness is not this P, is this K, right? Not for the complexity and all that. Here, just for the hardness of the optimization, right? So, of course, if you take a P and K equal 1, this is an easy problem. Why? And that you know, because that's a physics problem. That's simply a spin glass in a magnetic field, right? When K is 1, you're just taking the inner product with one vector. It's just a spin glass in a magnetic field. And that has been studied, and so the magnetic field will, in the right normalization, will help you get away from the equator and you will align. So that's an easy problem. But K equal 2 is a critical problem. And so, for instance, this P plus K has, for the moment, I'm presenting it just as a game, but you have this paper by Lenka, Florent, and others, I'm sure maybe in the room and forget their name, where you can look at it as a problem where you're given a P tensor and a K tensor, and you want, so if K is 2, that is if you have a matrix, you do a matrix PCA and a tensor PCA, in fact you are critical. Okay? If you do 2 tensor PCA, both larger than 3, then of course you're still hard. Okay, but if instead of giving you just a noisy version of a P tensor, I give you a noisy version of a P tensor and a noisy version of a 2 tensor, of this given by the same vector, then in fact you are in the critical regime. Now, what about the GLMs I mentioned? So so of course, so I mentioned a long list. So maybe I should go back to this long list and tell you which one are easy or hard or whatever. Oh God, it's too far.
online gradient system, you can just take many copies of the tensor with maximum.
Yes, you have IID. It's the same. Okay, you have an IID IID picture, and you just follow one at a time, right? That's
Right, like each of them has a large, like you could just sum them up and have much smaller noise.
yes, or you can just. Yeah, that's okay. So where is this? I'm sorry for that. I thought I had given an example, but a list of example, but no, it's very short. Okay, so you can imagine that when phi is linear, we are in the easy case. All the linear models are, of course, in the easy case. Phase retrieval is, in fact, critical. Okay. So same thing for this teacher-student network in general. Is just a matter of this. The derivative of this phi at the equator that will define it. So, for instance, mixture of Gaussian, so that's not on the sphere, but it's the same problem. Mixture, and we look at that, mixture of Gaussian is critical too. Many of the interesting problems are in fact critical, okay? And so in some sense, you know, I started this thing with tensor PCA, plenty of people tell you, yeah, but we don't care about this. Because most of the interesting statistics problems never fall into hard. And for a good reason. If they're hard, nobody touches them. You don't want to have this kind of, behavior where you need an enormous amount of data to do it. So the really interesting model, all the one that you are, phase retrieval, mixture of Gaussian, etc., are all critical. Okay, and so the important part is to understand, for these, maybe a little better. So for the moment, we have for online gradient, which is very simple. We have the same results for gradient flow. It's much more painful to prove, but the question is, of course, now, probably, I don't know, but online gradient could not be the optimal thing to do. Maybe you can do better. I don't believe that you can beat this mediocrity, this entropy thing, by having a better algorithm, whether you put momentum or this or that, larger batches. I think this difficulty will always be the same, right? So, and so, what?
You're saying that you have the same thing for the gradient flow? Because I actually take back the context about taking away the log and for the online. Now for the online, I think you need to keep it. But for the batch, that's the case I was thinking where it's not needed.
It's not written, so I will not put my hand in the fire for that, but I think yes.
You think you need it?
I think we need that. But again, it's our proof that needs it. Maybe our proof is not the smartest one. Who knows? Okay, so what are really interesting, of course, is to understand when you have the k equal 2, the information exponent, as we call it, to be 2, the critical thing, what is happening there. And of course, probably most of the things that are done in practice are in fact in the k equal 1 case, where it's easy to escape. And I think yeah? It will be critical, yeah. Yeah, yeah. But you see why, right? In this case, it's clear to see that, because of course it just means that the derivative in the direction of your x star will be very, very small if you take power 4. The first two derivatives will be 0 for reasonable losses. Okay, so your gradient flow, whatever you do, the gradient is just very weak at the random point you start from, and stays like that for a very long time until this component increases. And it takes very long. It's a very simple ODE thing. Look at the differential equation with this type of potential. And then look at how much time it takes. Forget just do dimension 1. Forget the spherical thing, just look at this. This is in fact the core of the proof, to bring it back to that. Okay, but this equation in 1D, then of course it will take a long, long time to escape. And the time will depend on how big is your initial x1, right? And because of course, if you start from x1 equals 0, this will not escape. But now, if your initial x1, you know it because when you choose something randomly, this x1 is the right normalization is like 1 over root n. This is what determines the strength of the lambda you need to escape. It's a very, very simple thing. Okay, so everybody can do this computation. It's not hard to guess. The hard part is, of course, to get rid of the rest, to reduce to this. Okay, so to answer your question, yes, if you take 4, it will be hard. Okay, okay. So I think I was a little too fast, but I will stop now. And then next time I might. So maybe just one thing. If you want to. So all that is super simple because our signal is, what you want to learn is one-dimensional. So it's clear to understand what the equator is, what the bad region is. It's clear also to understand what the dynamics, the transverse dynamics, because it's one-dimensional. When you really want to learn something harder than just one vector, you want to learn a more complicated function, your signal is, if the signal is ranked 2 or 3 or 17, you can adapt this. BBP can work with, and this for complexity, and what we've done with one dynamical system in dimension 1, if you're courageous enough, you can do it for a dynamical system in dimension 2 or 3 or 5. But if your signal has, more dimension and more structure, if the function you want to learn is more complicated, then it's not clear. Here you really have to understand, how you get away from this in a much more complicated space, and that we have. That is a really interesting question. So, for instance, for serious network with 2 layers, this is completely open, right? When you want to learn something more complicated than a rank 1 or a rank 2 thing, okay? No, but I think it's not only the size. I think the structure of what you learn, right? That will be important. I don't know how to choose. Here, it's clear how to choose the coordinates that points to where you want to go. When you want to learn a complicated function, this parametrization is complicated. Okay, so that, but there must be an effect of the same thing, which measures how hard it is to get out of it. Okay, so next time I will try to explain a little bit of the proof of all this, if you are game for it. Okay.